Only 4 chapters to go, guys. Acid base equilibria. If you haven't noticed yet, the entire purple packet is all acids and bases. So the first part, chapter 17, was just defining acids and bases, defining what we mean when we talk about strength, relating strength to the structure of acids and bases. Lecture 18 is just about applying what we know about Rice charts to acid-base equilibria. So doing calculations with acid and base equilibria. And then the third part, chapter 19, is going to be some applications. So understanding some of the things acids and bases do, how we can get more information about them experimentally. So that's the overview. So we're going to dive into doing some calculations today. So I just got a question about this. Seems really short. Chapter 18 seems really short, and the answer is yes. It is very short. So that doesn't mean the problem set's necessarily that short. Problem set 18 is 8 pages. So there's lots of equilibrium problems you can solve. But yeah, this lecture will be relatively short, and then the problem set is where the rubber meets the road. Even this lecture is going to be a lot of you setting up Rice charts and solving. The question was, how many days should we expect lecture 18 to take? I don't know. All right, so let's begin. Essentially, when most people think of acids and bases, a lot of people get this this term pH pops into their mind. Now the pH scale is essentially the way we measure the concentration of H plus in a solution. All right. I introduced in the last lecture that we use this little symbol P. So P of anything. We use that to mean negative log of that thing. So pH is going to equal the negative log of the concentration of H plus in a solution. The P stands for power, so pH stands for power of hydronium. Because when you take the negative log of something, when you take the log of something base 10, you get whatever the power is on that number written in scientific notation. So that's where the P comes from. Why do you think that we would, use the logarithm? Why wouldn't we just always report the concentration of H plus in a solution? Any ideas why we put things on these logarithmic scales instead of just reporting the numbers? The numbers in this case are really small, and most of us don't like numbers that are really small. So like 3.7 times 10 to the negative 8th, most people look at that number and they're like, that makes me, that's grody. I don't want anything to do with it. But then you say, oh, the pH is 7.2. Like, oh, 7.2? Why didn't you say so? So this just takes really small numbers and changes them to be like, 3, -1, 13. Makes them numbers that people are more comfortable with. Question. The question is the base of the log always 10? Yeah. So in general, and this might not go in math class, but in general in life, when you see just log, it's assumed to be base 10. And in science, you'll deal with log base 10, and so that'll always just be written log. Or you'll see natural log, which will be written ln, which is on the base of E, which some of you may know about, some of you may not. So the question is it just coincidence that the pH of water, neutral water, at room temperature happens to be 7? And that is kind of coincidence. We'll talk about that in a minute. So pH equals negative log of concentration of H plus. So for example, if concentration of H plus equals 1 times 10 to the negative ninth, then pH equals the negative log of 10 to the negative ninth, which is 9. Okay? So this property of logarithms you want to know, if pH equals negative log of H plus, then 10 to the negative pH equals the concentration of H plus. So these are two things you're going to want to know. You want to be able to go back and forth between those two, between pH and concentration of H plus. Now, with acids and bases, we had acid, which was represented by H plus, and then bases are represented by OH minus. So sometimes, we want to look at the flip side of things. Sometimes it's easier to deal with concentration of OH minus. And so we also invent POH, PO, as Sam just pointed out. Maybe what Homer Simpson in another language would say. PO! I don't know. So POH is going to be the negative log of the concentration of OH minus. And now, so we could also say 10 to the negative POH will equal the concentration of OH minus. Right, so those equations still apply, just like they did to pH. But there's going to be a relationship between these two. So we know that Kw, which is the equilibrium constant for the autoionization of water, which if you haven't watched lecture 17 yet, you don't necessarily know what that means. But Kw is the equilibrium constant for this chemical equation. Kw equals the concentration of H plus times the concentration of OH minus. That equilibrium expression is really the most important equilibrium expression in a water solution. And it turns out that at room temperature, this happens to equal 1 times 10 to the negative 14th. So at room temperature, this happens to equal 1.0 times 10 to the negative 14th, which means we can do a little logarithmation to both sides. I don't know. We can take the logarithm of both sides of that equation, and if you know the properties of logs, then you can predict what that turns out to be. This isn't a math class, so I'm not going to belabor the point. But if you take the negative log of both sides, what you get is the negative log of H plus the negative log of OH minus. What do we call the negative log of H plus? pH. You get the negative log of OH minus, which we call POH. And what's the negative log of 10 to the negative 14th? 14. So in a solution at room temperature, which is pretty much what we're going to assume the conditions are most of the time unless we're told otherwise, pH pH plus pOH will equal 14. All right. I believe all of these things are actually on your formula sheet, so you don't need to memorize them. But that's where this equation comes from. Yeah. All right. So the question is, based on this, we can figure out for neutral water. So if I just have pure water, in pure water, if I'm just looking at that, if the only equilibrium going on is water splitting up into H plus and OH minus. Oh, the stylus is having issues today. If we do a rice chart for pure water, water's a liquid. Am I going to care about that in my equilibrium expression? No, so I really don't care. Before water dissociates, I have no H plus and no OH minus. How much it dissociates, we'll call X. So I have equal amounts of H plus and OH minus in pure water. So I can actually just plug that into this equilibrium expression, and I get X squared will equal 10 to the negative 14th. So X equals 10 to the negative 7th. So what that tells me is in pure water, the pH is going to be 7. And the pOH is going to be the same thing, which is also 7. So the question is about, in chapter 15, when we learn to do rice charts. In pretty much all the rice charts we've done, we've kind of assumed that we had, an empty container to start. Most of them say, oh, there's an evacuated container, and you add some reactants. And this is the same. Here I was assuming pure water, so that water is the only thing around. All right. Now, what the rest of this chapter is, well, we know we can add things to water, and so then there's going to be other equilibria to analyze in the water solution. So if I add an acid, I'm going to have to look at a different equilibrium. If I add a base, I'm going to have to look at a different equilibrium. But what this allows us to establish, what this equilibrium between H plus and OH minus allows us to establish is, if I can find the concentration of one of those two, I can find the concentration of the other one. If I can find the pH, I can automatically know the pOH. It's very simple, 14 minus the pH equals the pOH. And if I can find the pOH, I can find the pH. So pOH is usually a tool. When you're reporting an answer, it's almost always going to be pH. Most people, when they measure the acidity or basicity of something, they want to know the pH. pOH is like a stepping stone along the way, because sometimes it's just easier for us to find the pOH and then subtract from 14. Okay. So, if we want to know the pH of a solution, we have different scenarios. The simplest scenario is, what if I have a strong acid or a strong base? So remember, to find the pH, any question that asks you to find the pH is really asking you to find the concentration of H+. So if I have a 0.5 molar solution of HCl, because it's a strong acid, what do I know about the concentration of H+ in that solution? It's exactly the same as the concentration of HCl, because if I dissolve 0.5 moles of HCl in a liter, then that's going to make 0.5 moles H+ and 0.5 molar Cl minus. So to find the pH, it's going to be the negative log of the concentration of H plus, which means the negative log of 0.5 Now, I don't expect you to be able to do logarithms in your head, but I do expect you to be able to pin a logarithm between two integers without a calculator. So, what two powers of 10 is 0.5 between? So we have 10 to the 0 equals 1, and 10 to the negative 1 equals 1/10. So 10 to the 0 is greater than 0.5, which is greater than 10 to the negative 1. So I know that this pH should be between what two integers? 0 and 1. All right. You should be able to do that, say on a multiple choice question. You should be able to pin the pH between two numbers, and then the actual value, yeah, you can plug it into your calculator. So the log of 0.5 is negative 0.3, so then the pH would be 0.3. 0.3 what? Someone calculate it? I thought someone had done it. Oh. Oh, you were talking about units. All right. So what is the log of 0.5? All right. 0.301. All right, great. I did have a professor in college who required students to memorize how to do logs in their heads. Well, it's pretty straightforward. You just have to memorize the log of like 2, 3, 4, 5, 6, 7, 8, 9. If you memorize those 8 logarithms, right, and you know which integer it's going to be between, then it's not that hard to do. But he used to call on students at random, and during class, and he'd say, "Oh, so this is the log of whatever," and he'd just point to someone. All right, tell me what that is. Yeah, it's not a skill I still possess, but his argument was if you want to go out and like get jobs as a consultant in the chemistry industry, and you can just do that kind of calculation in your head, you'll impress people and you'll be more likely to land jobs. Which is probably good advice. He's a very, very wealthy man. So find the pH of a 0.12 molar solution of CaOH2. What am I going to do with calcium hydroxide? This is a strong base. All right, Sam, what should I do? All right, I should calculate the pOH. So I need to know, to get the pOH, I need to know the concentration of OH minus. So calcium hydroxide is going to split up into calcium 2 plus and OH minus. What's the concentration of calcium 2 plus in this solution? 0.12 molar. And what's the concentration of OH minus? 0.24 molar. Because every time this dissociates, they get 2 of those. So now I could say the pOH is going to be the negative log of 0.24 0.62, all right? So then the pH would equal 14 minus 0.62. So 13.38. So if you've got a strong acid or a strong base, your calculation is really straightforward. How are things a little more complicated if I have a weak acid or a weak base? They don't dissociate completely. So there I have to figure out, well, at equilibrium, how much of it is dissociated. Oh, come on, don't moan. This is great. We get to use rice charts again. So if I have a weak acid, now figuring out the concentration of H plus is not quite as simple. Now I've got to first I've got to write the dissociation equilibrium. So for H plus, what are my products going to be? Or for HF, my products will be H plus and F minus. All right. And so, yeah, we don't know what the equilibrium constant is going to be. But if you grabbed a blue sheet on your way in, then it's right there. If you didn't grab a blue sheet on the way in, then I can give you one. All right, so where would I look on the blue sheet to find the equilibrium constant for this reaction? Monoprotic acids. HF is a monoprotic acid, so I'd look at the monoprotic acids. Oh, and is it on the slide? Oh, all right. So never mind. It's already there, and I wrote over it. I thought I had taken all the animation out of this so that everything would just show up at once. All right, I'll have to go erase that. So you have the equilibrium constant there. Ka of HF is 7.2 times 10 to the negative fourth. Go ahead. Fill in the information you know. Set up your rice chart. Solve. All right, help me fill this in for initial values. What can I fill in for initial values? 0.3. I'm going to do this in moles per liter. Moles per liter. And HF before dissociation is 0.3 molar. All right. Before dissociation, you know, the concentration of H plus in water isn't actually 0, right? We just found out that there is 10 to the negative 7th molar H plus in pure water without any acid added to it. As soon as you add acid, that amount that's in pure water becomes negligible anyway. So we'll just consider it to be 0. And there's no F minus before dissociation. All right, how much of it dissociates? X. All right, so this is going to go down by X. This is going to go up by X. This is going to go up by X. So I have 0.3 minus X. I have X and X. All right, now how am I going to figure out what X is? Not by subtraction. All right, Ka, one thing you notice if you look at your Ka sheets, most of the Ka values tend to be pretty small. This is kind of borderline small. So let's use the approximation, and then we'll decide if our approximation was decent. So we'll approximate that 0.3 minus X is still roughly equal to 0.3. That's going to make the math a lot simpler. So now the math becomes, well, I know Ka equals concentration of H plus times concentration of F minus divided by concentration of HF. So that's X times X divided by 0.3. 7.2 times 10 to the negative fourth. So X squared is going to equal something like 2.2 times 10 to the negative fourth. And then X is going to be the square root of that. Square root of 2.2 is going to be about 1.5. So this is going to be about 1.5 times 10 to the negative 2. All right. Then we've got to ask ourselves, well, even before I ask myself what the pH is this an acceptable approximation? So is 0.3 minus, well, 1.5 times 10 to the negative 2 is 0.015, right? Is that approximately equal to 0.3? It kind of depends on what your error tolerance is, right? You know, because this is 0.285. So the question is, well, according to sig figs, is it not still 0.3? Well, remember this was 0.30, so you know now it would be 0.29. Whether that's a valid approximation depends on how much approximation you can tolerate. To me, I'd say that's fine, but you may be in certain settings where like the pH requirements are much stricter, and so you can't be approximating that away. But I'd say most of the time we're going to use approximations with these. I think there's only like one question on the problem set where you'd be solving a quadratic, or yeah, maybe a couple. But most of the time we're going to use this approximation. So I'm going to say this is good enough for me. So then we got to answer the question. Now we know the concentration of H plus is 1.5 times 10 to the negative 2. So the last step is to say, okay, the pH equals the negative log of concentration of H plus, which is the negative log of 0.015. And the negative log of 0.015 is 1.5. Is that right? All right. 1.8. All right. Get comfortable with this process. You're going to be doing a lot of it. What questions do you have? All right. Weak base. Go ahead. Pyridine. I don't actually know this firsthand, but I'm told this is like one of the most disgusting smelling things you can smell. Pyridine? The question is, why does it smell so gross? Well, polar molecules with lone pairs on nitrogen tend to smell kind of fishy, and maybe this one partly because of its size and shape. The question is it circular? Yeah, the pyridine molecule. Pyridine looks like that. And if you're interested in molecules like that, then I've got a course for you next year. Yes, I've been like working on my marketing materials, so if anyone wants to give me feedback on the organic chemistry marketing materials, I will gladly accept it. You can take a look. So good question. We need an equilibrium. We need an equation to analyze. If we're going to do a rice chart, we need an equation to analyze. So rice. Well, bases, remember, are proton takers. So they're going to take a proton from water. So anytime you have a Kb, what you need to do is take your base, add it to water, because it needs something to take a proton from. So it's going to take a proton from water. When pyridine takes a proton from water, what does it become? C5H5N H plus. And what does water become? OH minus. So the equilibrium that you're going to analyze there is that one. So for a base equilibrium, we really need to include the water because otherwise the equation's not balanced. But when we actually do the equilibrium expression, is the water going to be included? No, so that column is always going to be basically a dead column. I will say this. I point this out in lecture 17. With acids, technically, we should be writing HF plus H2O makes H3O plus F minus. So with acids, water should be included in the equilibrium as well. But for shorthand, we usually leave the water out and write H plus instead of H3O plus. It just saves us a lot of time. But with bases, really the water needs to be included in the equation. Otherwise, the base has nothing to accept a proton from. Okay, help me fill in my charts. Initial 0.2 moles per liter of pyridine. All right. Initially, 0 of both of the products. How much does this reaction happen? X, so this will be minus X plus X plus X. All right, we have 0.2 minus X, X, and X. Look at my K value. What kind of K value? Small. Oh, gotta love those small K values. They just make life so much easier. So this is going to be roughly equal to 0.2. So when I set up my equilibrium expression, I get Kb equals concentration of C5H5NH plus times concentration of OH minus divided by concentration of C5H5N. So that's going to equal X times X over 0.2. So X squared over 0.2. And that equals 1.7 times 10 to the negative 9th. All right, so X squared will equal 0.2 times that. So that's going to be 3 point something times 3.4. times 10 to the negative 10th. All right, square root of 3 is going to be somewhere between 1 and 2, so x is, I don't know, 1.8 times 10 to the negative 5th. All right, so x represents what here? Concentration of OH minus. So the last part is going to be find POH, which is the negative log of that, which is 4.7. So the pH equals 14 minus 4.7. So that's going to be 9.3. Question? So the question is, why can't we use the concentration of C5H5NH plus to give us the concentration of H plus? Because C5H5NH plus, that's not H plus. It's different. It's got the H plus bonded to the pyridine molecule. When we talk about H plus in solution, we really mean H plus that's bonded to water itself. So H3O plus. All right, so with a weak base, there's one more step in the process. You just got to calculate the POH and then subtract from 14. Another question is, how did I get the KB value? It's on that blue sheet. How did they get it? Oh, well, we'll actually talk about how in chapter 19 we talk about how we can do a titration experiment to experimentally determine the KB value for a given base or the Ka value for a given acid. So those are all experimentally determined. Yep. What other questions do you have? All right. Let's make it slightly more complicated. So salts are ionic compounds that split up into ions when you dissolve them in solution. And sometimes those ions can act as acids or bases. So let's say you make a solution, 0.1 molar solution of ammonium chloride, NH4Cl. All right. Here I've actually ignored the sig figs rules and I just said 0.1 molar. I do that a lot just because I'm a little lazy about it. So even when I write a number with just one sig fig, I want you to interpret it as having 3. Let's just make that let's make that deal right now. So this is 0.100 molar solution of NH4Cl. All right. So the first question we got to ask ourselves is, well, what's going to happen when I dissolve NH4Cl in water? What's the first thing that happens when NH4Cl dissolves in water? It dissociates into, all right, this dissociates into NH4 plus and Cl minus. All right. So we have to ask ourselves, is one of those things going to have, or both of them, but usually it'll just be one, is one of those things going to affect the pH in some way? All right. So one proposal is Cl minus could grab H plus from water. All right. That would affect the pH if Cl minus grabs H plus from water. Do we have reason to believe that Cl minus is likely to grab H plus from water or not likely to grab H plus from water? HCl is a strong acid. And remember, when we say strong acid, we really mean super duper strong acid. So HCl, when you put it in water, the chloride completely dissociates from the H plus. So chloride itself is unlikely to go grab H plus. So this is just going to be a spectator ion. And we know that because it's the conjugate base of a strong acid. So the conjugate base of a strong acid is a non-base, essentially. It is non-basic. Because remember, when we say strong acid, we mean super strong acid. So the conjugate base of a super strong acid is a super weak, super duper weak base, non-basic. All right, so chloride's not going to do anything. NH4 plus. Could that potentially affect the pH somehow? I can give off H plus. NH4 plus, that acts as a weak acid. And you can confirm your suspicion that that might act as a weak acid by looking at your Ka list. All right, so what's the equilibrium I want to examine? Not NH4Cl. We've decided the chloride's a spectator ion, so let's leave it out of there. All right, NH4 plus can split into H plus and NH3. And do we have a Ka value for that? We do indeed. Ka equals 5.6 times 10 to the negative 10th. All right. So after a little more prep work, because we had to like think about which thing was going to act as an acid or a base, this problem just breaks down along the exact same lines as the last two. We've got our Rice chart. Fill in your initial, fill in your change, fill in your equilibrium, and solve. Let's see if you can beat me. All right, so I get to the point where I know x is maybe 7.5 times 10 to the negative 6th. 7.48. All right. Times 10 to the negative 6th. So the pH is going to be the negative log of that. Oops. So the pH is going to be 5.1. 5.1 something or 5.10? All right. It turns out actually when you take the log of a number, you can actually add another sig fig. If you actually take some numbers, and do the logarithms, you'll see like, you know, two numbers that are consistent to 3 digits, their logarithms will be consistent to 4 digits. But whatever. I don't want to talk about sig figs. Just do 3 sig figs on the AP test, and you'll be fine. I have not seen an example of a question where doing 3 sig figs on the AP test would have resulted in a penalty. So, all right. So, there you have it. That's chapter 18 in a nutshell. We'll do a few more examples, and we'll do some examples with pictures next time. But that'll be on the other side of vacation.